This question is from strength of materials for 2 marks. A thin-walled cylinder of radius r and thickness t is open both ends and fits snugly between two rigid walls under ambient conditions as shown. So basically this is a pressure wall of radius r and thickness t. It fits snugly. Snugly is the word which means that comfortably. So this pressure vessel comfortably fits between two rigid walls and the ends of the pressure vessel are open. The material of the cylinder has Young's modulus E, Poisson's ratio nu, and coefficient of thermal expansion alpha. What is the minimum rise in temperature delta T of the cylinder? Assume uniform cylinder temperature with no buckling of cylinder. Required to prevent gas leakage if the cylinder has to store the gas at an internal pressure of P above the atmosphere. Okay, so basically this is a question from the concept of pressure vessels, and the 4 options for this particular question are given. And according to the official key, the correct answer to this question is option C, delta T is equal to nu PR by alpha TE. Let's move on to the detailed solution for this question. Since the pressure vessel is subjected to a minimum rise in temperature where the change in temperature is delta T, as a consequence of this, there will be a change in dimension. This change in dimension is nothing but delta L is equal to L alpha delta T, where L is the length of the pressure vessel, alpha is the coefficient of thermal expansion, and delta T is the rise in temperature. From this expression, when we bring the length of the pressure vessel to the left hand side, it becomes delta L by L is equal to alpha delta T. So this delta L by L is nothing but strain in the length direction, and that is obtained because of temperature limits or temperature change. So that is why that strain in the length direction is called as a thermal strain, which is epsilon L is equal to alpha delta T. Since we know the thermal strain in the length direction, we will generally use the generalized Hooke's law, which gives the relations between stress, strain, Young's modulus and Poisson's ratio. So according to the generalized Hooke's law, we can write epsilon L is equal to sigma L by E minus nu into sigma H by E, where nu is the Poisson's ratio and sigma H is the stress developed in the radial direction of the pressure vessel and E is the Young's modulus. Since it is given that both the ends of the pressure vessel are free, then the pressure vessel will be free to expand along the length, so there will not be any stress in the length direction. So thermal stress along the length of the pressure vessel will be 0. Substituting this condition in this equation will give us thermal strain in the length direction is equal to minus nu sigma H by E. Remember that this negative sign is just to show that there is a decrease in dimension because of the temperature limit. Okay. Keeping that aside, we know that for a cylindrical pressure vessel, hoop stress is given as PD by 2T, and we know that D is equal to 2R. Substituting that will give us hoop stress sigma H is equal to PR by T. When we substitute PR by T in this equation, neglecting the minus sign, we get epsilon L is equal to nu PR by TE. But we know that epsilon L is equal to alpha delta T. Substituting that will give us alpha delta T is equal to nu PR by TE, and rearranging the terms will give us delta T is equal to nu PR by alpha TE. So that matches with option C.